Greetings of the day to everyone. The topic for the presentation is in vitro diffusion studies of nanolipid carriers of routine for brain targeting through nose. Application of Box-Behrenken design. Here I will straight away move ahead to the introduction part where I will be explaining the purpose of the study. Drug of choice is rutin, which is a potent flavonoid proven to possess antioxidant, anti-Parkinson activity with low bioavailability when administered through oral route. Nanolipid carriers are the colloidal carriers that were developed in the previous decade as an alternative for existing traditional carriers. Due to their tiny size, nanolipid carriers are easily penetrated into small capillaries, which can be taken up within cells for efficient accumulation at target site. Intranasal delivery is a proven strategy for rapid reaching of drug to target site and provide fast onset of action. By avoidance of hepatic first pass metabolism, easily accessible, highly permeable at the vascular site by surpassing blood-brain barrier. Box-Behrenken design, a three-factor, three-level screening approach is used to evaluate interaction effects of formulation variables on measured responses of the prepared formulation. Routine BCS class 2 drug which is having low solubility and low bioavailability. To increase its bioavailability, we are trying to formulate nanolipid carriers having high drug loading capacity can enhance therapeutic effect, site-specific action and improved bioavailability. The main aim of the present study was to fabricate routine-loaded nanolipid carriers for efficient delivery to the brain through the nasal route by applying Box-Behrenken design. Objectives to formulate routine-loaded nanolipid carriers for brain targeting by the design of Box-Behrenken and to carry out in vitro characterization including drug release to optimize and validate formulation using Design Expert software version 13. Layout for Box-Behrenken design. Here, the lipid concentration, surfactant concentration and sonication time were picked as independent variables. Each independent variable was analyzed at three levels: low level, medium level and high level. Total 17 formulations was prepared based on this layout prepared by this method. Melt emulsification followed by the probe sonication method. Lipid phase consists of drug. In each formulation, 10 mg of drug was taken. Glycerol monostearate, which is solid lipid. Oleic acid is a liquid lipid. Aqueous phase consists of polaxomer 407 and distilled water. Both phases are heated to 70 degrees centigrade. The addition of aqueous phase to lipid phase at 70 degrees centigrade under magnetic stirring, followed by sonication, and obtained nanolipid carriers are further freeze-dried. The particle size and entrapment efficiency was also evaluated by using standard methods. Diffusion studies. The studies were performed by using French diffusion cell. In a donor compartment, the nanolipid carrier formulation was taken. In receptor chamber, the phosphate buffer pH 6.4 was filled. Between the donor chamber and receptor chamber, the pre-soaked dialysis membrane was placed. The studies were performed for 24 hours. The aliquots were withdrawn at periodic time intervals. After suitable dilutions, the concentration of routine diffuser was analyzed by UV spectrophotometry with the help of calibration curve plotted, and then percentage of drug release was calculated. The in vitro drug release of routine nanolipid carriers was shown in plot. The graph was plotted between the percentage drug release and time. As a result, the in vitro release of routine from routine nanolipid carriers was within the acceptable range of 10 to 15% prediction error. Total 17 formulations were plotted like this. Formulations according to Box-Behrenken design along with the results of the three responses. Each parameter was analyzed 3 times and its average was taken. This model was fit into DOE software and from this the equation was obtained. Whereas Y1 and Y2 are the responses of particle size and entrapment efficiency, currently our present topic is in vitro diffusion studies. So I am going to explain on Y3 drug release equation. The effect of 3 independent variables on in vitro drug release can be explained by this equation. Whereas here positive sign indicates increased effect and negative sign indicates decreased effect. Individual effects A, B, C A is the lipid concentration. While increasing the lipid concentration, the drug release is decreased. While increasing the surfactant concentration, the generally drug release should be increased, but here the drug release is decreased. This is due to the higher surfactant concentrations tend to form mycelia with the drug and therefore reduces the surface area, which reduces the drug release. C is the sonication time. At high sonication time, the particle size decreased and surface area increased, drug release is increased. Interactive effects A, B, AC and BC. The interactive effect of C with A and B becomes negative even though the individual effect of C is positive. A square, B square and C square are the multiple effects. At high levels of lipid, high levels of surfactant concentration, there is no change in relationship between the drug release and their concentration. But at low levels, C showed positive effect. At high levels, multiple effects, C showed negative effect. The reason behind this is at higher speed, the particles may hit the wall and come back to its position. The particles may show the adherence, which reduces the surface area. Therefore, the drug release is decreased. Based on this polynomial equation, the order of influence of the independent variables on drug release is sonication time greater than the lipid concentration greater than surfactant concentration. The results which I have explained from equations is itself depicted in its respective response surface plot, whereas A represents the effect of individual lipid concentration on drug release. B indicates the individual effect of surfactant concentration on drug release. C indicates the individual effect of sonication time on drug release. The interactive effects can also be explained by these response surface plots. The method was statistically analyzed by ANOVA and the model shows significant for all the three parameters taken. Desirability for the optimized formulation is 0.89. It shows that highest better desirable characteristics are obtained for this optimized formulation. Based on this optimized formulation, we can know the optimized formula concentration and their responses predicted values. Optimized formula by box-band design for routine nanolipid carriers. Whereas the lipid concentration is 0.29 grams and surfactant concentration 0.510 grams. Sonication time 40 minutes. Responses and their predicted values are particle size 104.3 nanometers, entrapment efficiency 92.1%, drug release 45.9%. The optimized formula was prepared based on these concentrations and evaluated. There is no much difference between the predicted values and experimented values. The in vitro drug release for the optimized formulation was within the acceptable range of prediction error 10 to 15%. The prediction error was calculated by experimental values minus predicted value by experimental value into 100. Finally, conclusion. Routine loaded nanolipid carriers were successfully designed, optimized by applying box-band design using Design Expert software version 13. Present work revealed that optimized formulation developed by design model is significant. Routine nanolipid carriers may be a successful approach for boosting effect of routine in treating Parkinson's disease through intranasal route. Future prospects, it will be further studied in ex vivo and in vivo using animal studies, for which approval is also obtained. Thank you all.